Hi and welcome to Cherry Pie Math. This video is going to go over compound events. Before we get started, you should know what probability is, like the definition of probability, and you should be able to convert from fractions to decimals to percentages and back. So like percentages back to decimals, back to fractions. So to get started, we're going to do just a little activity. I want you to think about what's the probability of rolling a 1 on a dice, and then what's the probability of rolling a 1 and then a 4 on that dice. So you're rolling it twice and you want to get a 1 the first time and a 4 the second time. What's that probability? We are going to answer this later in the video, so hold on tight, but just pause the video and kind of think about it. What do you think the answer would be? So just a reminder to calculate probability, and this is the notation. We write P and then parentheses, whatever we want our success to be. In general, we just write N. I don't know why N. Decide maybe for like number, N for number, but this is just kind of what we would write in the general mathematical world. So the probability of N happening, or whatever our success is the number of desired outcomes, or the number of things we're looking for, over the number of possible outcomes. So that's just how we would calculate it. So if I was trying to roll a 1 on a 6-sided die, like just the 1, it would be, or actually let me change the number. If I was trying to roll a 3, 3 only appears once on a 6-sided dice, and so it would be 1 over 6 because there's only one possible outcome that we're looking for over, one desired outcome over 6 possible outcomes that I could have. Compound events, and I kind of filled this out beforehand, are multiple probabilities happening separately in quotation marks. They can happen simultaneously, but it would be it'd be kind of like rolling 2 dice at the same time, where they aren't really interacting with each other per se, or it's things happening in succession. So like you roll something once, and then once you're done with that, then you roll again. So compound events is the opposite of single events, basically, where you just have more than one probability happening. And we can represent them as lists, trees, tables, or we can simulate it. Simulating is how you would calculate them, especially like in the sports betting world. But because we're just learning about it, we're going to do most of these by hand. There are 2 kinds of compound events that we're going to be learning about. One is independent and the other is called dependent. Independent events are where the outcome of one probability or the outcome of one event does not affect the second event. And then for dependent, obviously it's just the opposite of that. So it's where the outcome of one event does affect the second. So some examples of this, independent would be like flipping a coin, for example, because if you flip a coin, technically there shouldn't be any influence on the second time you flip a coin. Or like rolling a dice, when you roll a die once, it doesn't affect what's going to happen on your next roll. They're called independent events because they have no bearing on what happens the next time you're going to do the same probability. Dependent events is like, let's say you have a deck of cards and you take a card out of the deck and you don't put it back. That does change the probability of the second event because now you have less cards. So if I was trying to find the probability of drawing a heart, the first time would be 1/4 because 13 out of 52 cards. Yeah, 13 out of 52 cards are hearts. But then the second time I do it, because I'm down 1 heart, providing that this first one worked, now I have 12 hearts instead of 13, so it would be 12 out of 52, and you would simplify that. So that's the idea of dependent events, is where the second event is now different because of what happened in the first one. So let's do some examples, not just of finding what is independent and dependent, but also actually calculating these compound events where you have more than one thing happening at a time. The first example we're going to do is with lists. So Ellie has 4 things to pack for her lunch: a sandwich, carrot sticks, apple slices, and a muffin. What is the probability she packs it in the order carrot, muffin, sandwich, apples. This is a dependent example. Dependent. Because if she puts in carrots first, like carrots, that's 1 out of 4. That's the first event happening. The probability of getting carrots first is 1/4. Now, the second thing that she puts in is actually going to be 1 out of 3 because there's no longer carrots in that factor, right? So this would be dependent because the second probability is different than the first probability. It's been affected because of that first probability. So I went ahead and I made a list of all the possible options that we can get. So let me go ahead and paste it here. And I didn't even realize when I made it, but it says scam. That's so cool. Okay, so this stands for sandwich, carrots, apples, muffins. And these are all the possible ways. There's a fancy word called permutation that just basically means the order. But these are all the different orders that I can have, or that Ellie can have when she puts things in for her lunch. We want to have CMSA. That only occurs right here. So that's, and remember, when we're calculating probabilities, it's the number of desired outcomes over the number of total outcomes possible. So out of all of these, I only have one thing that matches what I want. The carrots, muffin, sandwich, apples. That's right here. And there are 24 total outcomes possible. So the probability of CMSA is 1 out of 24. And you could leave it like that because it is, what's it called? It is simplified. But if you wanted to change it to a percentage, which I think is preferable, you would just do 1 divided by 24 and it becomes 4.17%. And that's just rounding. And there you go. So pros of the list, it's very clear to see where your answer is. The cons is making the actual list. Because I just pasted it, we didn't really get to see the process. But basically, I had to start with every single option and then be able to move these 3 around. So what I would do is I would keep the first 2, and then I would switch these 2 around here. And then I would change the first or the second one there. And you just have to make sure you keep track of every single option. It's super annoying. I wouldn't recommend it for more than 4. If you have 4 separate items, you're going to have, let me actually write this. So if you have one option, obviously there's only one order. If you have 2 things, there's 2 ways to do it. If you have 3 things, there are 6 ways to have it. And if you have 4 things, there's 24 ways to have it. If you want to take a screenshot or write that down, maybe that will help you make sure that you have all of those options when you're making a list. But like, as you can see, it jumped super high from 3 to 4. It's super annoying. Don't recommend it, but you might have to do it anyway. The second one is my favorite. This is called a tree diagram. And you'll see why in a second. These are useful for organizing information. And yes, I write my Z's like this. That's like the cursive way of writing a Z. I just think it looks cool. Anyway, what is the probability of drawing a red card twice in a row from a standard deck of cards without replacement? Because it's without, that's going to be dependent again. Because you're changing the amount of cards in the second time, okay? So the probability of drawing a red card twice in a row from a standard deck of cards. So the first time, okay, actually, let me start here. So we have the deck, and we have 2 possibilities. We can have a red card or a black card. And this is a 50% chance, or 1/2, each time, because, what am I going to say? Because there's an equal amount of red cards and black cards, right? Remember, a standard deck of cards has 52 cards. In the first one, if I drew a red the first time, now there are only, instead of having, 26? Instead of having 26 red cards, I only have 25 red cards. And that's actually going to go over here. Now I only have 25 red cards out of 51 cards total, because I managed to draw a red the first time. And then if I was to make this for all of them, so this is why it's called a tree diagram, is because it shows us a tree. pretend these are branches. And what I love about the tree diagram is it's really helpful for organizing, okay, the first time I can have red or black, and then the second time this is what can happen. It doesn't have to be the same. Sometimes you'll have a different series of information for the first time versus the second time. Anyway, let's go back to the question. Okay, so the first time we have a half chance for red or black. The second time, if I drew a red card, now I have 25 red cards and 51 total cards. If I drew a red card, the probability of getting a black card the second time would be still 26 because there are still 26 black cards because I drew a red card. That's what that's saying. The first time I drew a red card, but there are still only 51 cards because I did not replace that card in the first place. Similarly, in the second way, if I drew a black card the first time, then the second time I still have 51 cards. All of these I only have 51 cards left because I drew a card the first time. But if I drew a black the first time, now I have 26 red cards still, and to draw a black twice in a row would be 25. And you can kind of see this is a mirror image because we are using the same cards for both scenarios. I only care about drawing a red and then drawing a red. If you have a tree diagram, the way you would do it is you would have this multiplied by this. You would basically find, okay, I'm going here and then here, and then you would take those probabilities. So I have 1/2, and then I have 25 over 51, and you would multiply them together to get your final probability. So let's see. So the top would be, since you're multiplying, you just multiply across. So 1 times 25 is 25, and then 2 times 51 is 102. And then we are going to simplify it. So even though like you can't like reduce the fraction, you can still, or not simplify, sorry, you can make it into a decimal and fraction. So 25 divided by 102 is about 24.5%. So that would be the probability of getting 2 red cards in a row, which makes sense. You know, it's about a quarter of the chance because there's really just red or black, right? So there's like 4 kind of options happening. But it is a little bit different. So you just have to be careful. So I really like the tree diagram because it helps me keep track of the information way better than a list does, because the list is super annoying, but the tree is really nice to kind of keep track of what's happening. The third example we're going to do is a table. This is also useful for organizing information, but this will take longer. So like, what's the probability of rolling double sixes, for example? And this will actually go back to our original question, what's the probability of rolling a 1 and then a 4? So we're going to make both of these. So like what you would roll, the probabilities of rolling, or the potential things you can get. So each of these represents one dice or one roll, I guess. So that's roll number 1 and that's roll number 2. We'll do that. Roll 1, roll 2. It really doesn't matter which order you take. So this would be 1 and 1. This would be 1 and 2. This would be 1 and 3, 1 and 4, 1 and 5. And you can kind of see, let me just try to copy these actually. It'll save me some time. I hope you guys are having a good week. I am having a good week. I just started teaching piano lessons this week. Okay, even though I teach math too. So then I would have 1, 2, 3, 4, 5, 6. And I'm going to copy that as well, so I don't have to keep writing this over and over and over. Okay, so I have my potentials. We are looking for the probability of rolling double sixes. The only time that happens is here, and that's kind of like how we had in the list. It's only 1 out of 36, so it'd be 1 out of 36 is the probability of rolling double sixes. Similarly, the probability of getting a 1 and then a 4 would be 1 out of 36 because it's 1 out of the 36 options here. Yeah. If I was to say what's the probability of rolling a 1 and a 3 in either order, that would be 2 out of 36 because that happens twice if we're not caring about the order. But if you care about the order, then it would only happen once. So the table is basically like the list, just a little bit more organized, but it's really hard to do if you have more than 2 things happening at the same time. There is a different kind of probabilities. Let's say 40% of the population has type A blood. What is the probability you need at least 4 people to find one with type A blood? So we're going to split the screen. Okay. And then we're going to say there's 4. And we're going to say the probability of getting tails is 40%. Because the probability, we're looking for the probability that it would take at least 4 people to get type A blood. So in this case, we're basically saying type A blood is like getting tails. We want to see how many times does it take to get tails only on like the 4th try. So let's see. Nope, that one we got it right away. That one, again, that would only be on the 3rd try. Okay, so this one only took us 3 times. So this one took us 3 times. Let's try it again. Nope, 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 nope. How many is that? 1, 2, 3, 4, 5. Nope, 6. Nope, 7. 8. That one took us 8 times. So simulation is nice because it kind of tells us more about the experimental probability versus just the theoretical probability, although we could calculate the theoretical probability as well. But with simulations, you would have to do it a couple of times just to get a better idea because the first time we only needed 3 times, but the second time we needed 8. Okay, so some things to remember. All these probabilities are found because we found the number of desired outcomes out of the total possible outcomes or possibilities. Even when we were doing like the tree diagram, that was just kind of a shorthand way of doing all of those. So if I wasn't to do that, then I would have had a list of 102 different ways of that turning out, which no one wants to write a list of cards 102 times. But that's essentially what we're doing, is we're finding the number of desired outcomes over the number of possible outcomes. With compound events, it just means that we have more possible outcomes out there. And if you have more than one probability in a row, you just multiply the probabilities together. I can't spell today. My goodness, multiply. You multiply the probabilities together just like we did in the tree diagram. Anyway, I hope that is a good overview of how to do compound events, and good luck.